Okay, we're going to continue talking about disinfection today, and then some ancillary water treatment, miscellaneous things that happen after disinfection, and then I'm also going to introduce the research project for the course. Remember that homework 7 is due on Friday. Have any of you already finished that assignment? Homework 7? Not yet? Okay. Well, I never do anything without a deadline, so I totally get it. The other announcement I wanted to make was that remember the career fairs today. So if you haven't already stopped over to that, I would really encourage you to go over after class and just see which companies are available and what opportunities maybe are interesting. Even if you have a job lined up currently or if you aren't planning to do an internship, I think it's good just to become familiar with who are the people and companies that are interested in hiring at Marshall. So that's where I'm going after this, is over to the rec center. That's until 4 o'clock today. Does anybody have any announcement related questions before we continue talking about disinfection? Okay, so in class on Monday we were talking about how it's the concentration multiplied by the time of exposure that is the model that describes how much disinfection is needed for different types of microorganisms you're trying to target and for different chemical disinfectants that you might use. So using chlorine dioxide as an example. If you have the trend of warmer water, you can see that a lower dose is needed, and by the way, the units here for these numbers like 63, 26, 23, and so on, that is the concentration in milligrams per liter multiplied by the minutes of contact time. So with this model, just for instance, if you had 5 degrees Celsius water and you only had 1 minute of contact time before you needed to consume the water or before you needed to move it out of the contact chamber and into the distribution network. So 1 minute at 26 milligrams per liter would achieve the same thing in theory as 26 minutes of exposure multiplied by 1 milligram per liter of contact time. So this assumes that there is to some extent just an exchange between the two of contact time and concentration, but the product of the two would need to reach this overall dose in order to achieve 3 log inactivation. Has anybody ever heard of Giardia before? This pathogen Giardia? People sometimes get exposed to Giardia when they are on backpacking trips, or if they're spending time in the mountains and are drinking from creeks. It's called, the disease that sometimes you get from Giardia is called beaver fever, because beavers are well known for harboring Giardia in their own gut. And it's the sort of thing that causes vomiting, diarrhea, dehydration, feeling pretty terrible. And it's considered a difficult pathogen to disinfect against because it forms a spore. Like, it's a very hardy pathogen. Viruses are relatively easy to kill in drinking water because they're so small. The chemical disinfectant can penetrate through them very easily. They don't have a very rugged cell wall. They're just, viruses are strands of DNA. The same thing with bacteria. They're small, they're weak, they're easy to inactivate. But the thing that we have to be more attentive to are these tough microorganisms that maybe have a thick cell wall or can form a cyst or are embedded in a spore. And so Giardia is one of those kinds of like difficult to inactivate pathogens. Cryptosporidium is another type of pathogen. And so looking at these tables, which of the two do you think is tougher, Giardia or Crypto? Like, which of them is more resistant to being treated with a chemical disinfectant? Crypto is tougher. And what are the clues that how did you come to that conclusion?
Higher concentration per ton, times time.
You need more concentration time, more CT, and that's even to achieve less inactivation. If you notice the table here for crypto, this is just to achieve a 2-log inactivation. So 99% kill, it takes 858 milligram per liter minutes. Whereas Giardia, you can get 3 logs of inactivation for just 26. So crypto is a very dangerous microorganism because it's resistant to some of the types of disinfection that we use. So ozone, chloramine. You can see that chloramine is a much weaker disinfectant than, say, ozone or chlorine dioxide. So you may wonder why people would even bother to use chloramine if you need such a high concentration times time. The nice thing about chloramine is it's more stable in water. So if you remember from Monday, we were talking about like, what are the characteristics of a perfect disinfectant. A perfect disinfectant would be one that has a good residual. After you treat it, it stays in the water, and chloramine is more stable. So people like chloramine in the sense that it provides good residual protection. So sometimes they'll take like a balanced approach where they would have both chlorine and then also chloramine. And the chlorine gives you like the fast, powerful disinfection. The chloramine provides residual protection. Chloramine is also thought to be less prone to forming disinfection byproducts, which can be potentially harmful carcinogenic compounds that when you've got organic material in water, if you add chlorine to it, and by organic material what I mean is like, let's say you had some leaves in your source water. If you're taking water from a pond and leaves were falling into the pond and the leaves decay, they fall to the bottom of the lake, it's just kind of like a murky muck that gets dissolved in the water. So it's some organic, meaning carbon containing material, and so the water has just a little bit of dissolved carbon in it, organic material. If you then oxidize it by adding a chlorine disinfectant, then it can form disinfection byproducts that are known to be cancerous to humans. So people would use chloramine for that reason. What about this question, which disinfectant is the most powerful between these three? Well, it would have to be ozone, because ozone is the one that uses the lowest dose to achieve the same 3-log inactivation results. So ozone's powerful. Does anybody remember what's the downside of ozone? We talked a little bit about ozone on Monday. What is it bad at? Yeah, it does not provide residual protection. It's not stable. It breaks down within 5 or 6 seconds. So it's great for the inactivation, but it's not providing protection over the long term. So when you're adding chlorine to water, oftentimes chlorine gas is used as a source. If you've got a really large water treatment plant, chlorine gas would be common because it's the most inexpensive and efficient way. Like those big gigantic 1-ton chlorine cylinders, you can treat a lot of water with a ton of chlorine. Whereas if you're using a liquid chlorine source like hypochlorous acid or sodium hypochlorite, those are safer. You know, like if you have a spill of a liquid, that's not quite as dangerous as a chlorine cylinder rupturing. That would be really considered like a panic moment if one of those chlorine tanks tips over and suddenly is discharging gas into the atmosphere. So bleach is safer, but you have to use more of it. Chlorine dioxide is nice because it can be generated from salt. They can just use salt and then an electrical process that forms chlorine dioxide gas on site. And so you're bringing in a raw material that's very stable. It doesn't break down over time like bleach does. Like when you've got liquid bleach at high concentrations, it just naturally decays, even if you're not exposing it to anything. Whereas if you bring in salt, it's not going to decay, it's not dangerous, and so you can generate the chlorine dioxide on site. Of course, it's using electricity, so then it can be costly in that sense. It's pretty common in chlorination that you would be adding a certain amount of chlorine and you'd be seeing the the concentration going up in the water, but then the concentration would come down as it actually does the work of oxidizing organic material and disinfecting the water. So some of the chlorine that you add is consumed, and then you need to kind of follow through that peak of the chlorine concentration, and you're continuing to add more and more chlorine, and the chlorine concentration is going down, oddly. And then the stable residual you can expect to be present is when it starts to go back up again. And so this curve is called the breakpoint chlorination process, which is just the idea that adding the chlorine doesn't necessarily ensure that there's a certain amount in the concentration of the water. So the amount of chlorine applied goes down for a little while as it's being consumed through the disinfection process. UV is a special interest of mine as a drinking water disinfectant. I did a lot of work during my PhD time at Purdue on UV as a disinfectant for water and for wastewater. And the interesting thing about UV is that unlike chlorine or chemical disinfectants, UV doesn't actually kill the pathogen. It just inactivates the pathogen so that it can't replicate if you drink the water that has the contamination in it. So, for example, if you have water with bacteria in it and you chlorinate the water, the bacteria is dead. So what you're drinking is a dead, destroyed bacteria particles. They're still there, but they're not going to make you sick because the bacteria can't reproduce inside you if it's dead before you even drink the water. On the other hand, UV, it does not kill the microorganism, but it makes it so that it's not able to replicate into the next generation. So it's kind of it's strange to think that you'd be drinking water that has a virus in it or that has bacteria in it, but it's not going to make you sick because the virus and the bacteria has been inactivated. UV offers some nice advantages compared to chemical disinfection. It's considered safe because there's no chemicals to spill. It provides protection in a way that, remember that certain pathogens that are very hardy, like Giardia and Crypto, that have a spore or can form a cyst, that they can protect themselves with a thick cell membrane against the chlorine. They can't protect themselves against the UV. It penetrates through, and it's able to inactivate things like Cryptosporidium that otherwise would be really difficult to provide protection for. So you can use a complementary approach of both UV disinfection and also chemical disinfection. And about 20 years ago, after the big outbreak in Milwaukee that I've told you about, where they had an outbreak of Cryptosporidium and about 500,000 people got sick, the EPA started to mandate that community water supplies should provide additional protection against those disinfection-resistant pathogens. And so UV has become a lot more popular in the last 20 years because it does provide it provides a way of inactivating microorganisms that aren't going to be necessarily addressed with chlorine disinfection. Some of the downsides of UV is that there is a little bit of regulatory uncertainty associated with calculating the dose of UV that's applied. It's not as easy as the concentration times time model, because in a chlorine contact chamber, as long as you get the chlorine evenly distributed in the water, if it's well mixed, then all of the water has an equal amount of protection. But when water is flowing through a UV disinfection reactor, some of the water particles are close to the lamp, some of the water is far away from the lamp, and the further away it is from the lamp, then it's going to get less UV exposure. And so it's kind of tricky to calculate the average trajectory of all the particles that flow through a reactor, and trying to determine the dose in a UV reactor is a lot more complicated than just simply multiplying an average concentration times a reaction time. And then another issue, well, I'll show you a picture of these lamp sleeves can get fouled, meaning that when you dip the water around the lamps that the UV is generated from, then sometimes an organic or an inorganic, like calcium carbonate, magnesium, precipitates can form on the outside of the quartz lamp sleeves that encase these lamps. And if there is like a mineral coating on the outside of the sleeve, then the light can't get through any longer. So this is what those reactors look like. Water flows through a pipe, and then it goes through another section of pipe. It's pretty common to have a cylindrical shape for the reactor, and you'd maybe have multiple lamps. You can see that there's the wires going into each of these lamps. It looks like this has 1, 2, 3, 4 lamps here. And then it would be common to have some sort of a squeegee, in a sense, like a lamp sleeve wiper. Sometimes it disperses a chemical that is wiping down the lamp sleeves, maybe like an acidic substance. Sometimes it's just abrasive, and it's like a wire mesh that goes over the quartz to kind of keep the mineral accumulation from blocking the light. But how long the water spends in the reactor and the intensity of the UV radiation is similar in a sense to the concentration times time approach with chemical disinfection, but just the tricky thing is knowing what's the intensity of light that a particle is experiencing as it travels from the influent pipe to the effluent pipe, because a different particle may have a trajectory that goes really close to the lamp and it gets lots of good exposure, and then there may be some of the water particles that come in, and just because of statistics, a small number of the particles that go through won't get very much intensity and will maybe pass through very quickly. So you have to do a lot of testing to find out the distribution of dose in a UV reactor. And the interesting thing, the way that the UV reactors work, is that they actually fuse together parts of the DNA in the target virus or bacteria or Giardia, crypto. What they're doing is the UV light penetrates through the cell wall, and then it just so happens that DNA consists of 4 base pairs, and when you have adjacent thymine, so it's one of the 4 codes in DNA. If you have 2 thymines together in a DNA strand, then the UV light can fuse them. It's called a dimer, where basically it's causing 2 adjacent thymine base pairs to melt together, and then when the cell is trying to replicate, it's like a corrupt file. So it's like if you had a USB jump drive and somehow it was close to a magnet and it just basically scrambled the data. The UV radiation has a way of fusing together the DNA so that then the virus or pathogen is not able to reproduce. So this is a table that illustrates the credit that you'd get for a certain UV dose in terms of the removal of crypto, Giardia, and viruses and so on. So you can see that 1 log credit, that means 90% removal. So you can achieve 90% removal of cryptosporidium by a dose of 2.5 millijoules per square meter. So that is the amount of energy over a certain surface area, is how the intensity of UV is described. Intensity times time. So joule is a watt per second. So a pretty typical dose that they're trying to achieve in a UV reactor is about 40 millijoules per square centimeter. And so a dose of 40 millijoules per square centimeter is going to give you a lot of removal of crypto, Giardia. There are certain viruses, like for example the adenovirus, which causes colds, is just one that I guess it's maybe because it doesn't have very many adjacent thymine dimers, or it may be something related to the structure of that virus. But there are a handful of viruses that require a really high UV dose. But luckily, those same viruses are pretty vulnerable to chemical disinfection. So if you use the UV to mainly focus on crypto and Giardia, and you use chlorine to focus on viruses and bacteria, then you'll have a good kind of multi-layer approach to disinfection. So just to get a sense for how these calculations work with UV, I wanted to show you this example where let's assume that we have a 1 meter long reactor and it's cylindrical in shape and the inside diameter of this reactor is 25 centimeters. Then what we want to find out is what lamp power would be needed in order to achieve this target dose of 40 millijoules per square centimeter. And part of the thing that makes it a little bit tricky is we've got this lamp and it's inside of a pipe and the light is shining out in all directions. And if you're close to the lamp, then the intensity is higher than if you're far away from the lamp. The further away you get from the lamp, the intensity is lower. And so the worst case scenario is that a fluid particle comes into the reactor and just skims along the very bottom the whole time that it's in there. And so if we wanted to be able to ensure that a particle that is at the outside edge is receiving that dose of 40 millijoules per square centimeter, then what we need to do is we need to find out what is the intensity of the radiation over the area of the cylinder, the inside reactor area. And so the area that's going to apply is going to be the circumference of a circle multiplied by the length of the reactor. So if you think about the cylindrical reactor as similar to like a soup can, you know, soup cans have a paper label on the outside. If you cut that label and then laid it out flat, you could easily measure the area of the label. So the area that we want to be thinking about is the circumference, the outside area of that, multiplied by the length into the page. The 1 meter long cylindrical shape of that gives us the area. So the area that would apply here would be pi d for the circumference, pi times d, and then multiply that by L to get the overall area. So in this case, the diameter of the reactor is 0.25 meters, and then the length of the reactor is 1 meter. So the surface area that the UV is acting around at the worst, you know, at the furthest most point that the water could be, the overall area that the intensity is acting over is 0.7854 square meters. And that's the same as 7854 centimeters squared. And the units here, 40 millijoules per square centimeter, that is the same as 0.040 joules per square centimeter. And so we want to know what is the overall power. Then it's going to be 0.040 joules per square centimeter multiplied by the area. And so it would be 0.040 joules per square centimeter multiplied by 7854 centimeters squared. So that's 314.2 joules that has to be applied. And we assume that the exposure time is 1 second and the lamp is 30% efficient. Like the 1 second exposure time, you control that by the flow rate of the water into the reactor. We want to assume that the water particle is going to spend 1 second inside of that reactor. So if the exposure time is 1 second, then that means that we need 314.2 watts. Because a watt is a joule per second. So the 30% efficiency then means we have to divide by 0.30. And so the input power required is 1,047.2 watts of input power. And you know, that's about as much electricity we could get out of a normal plug. You know, this is not a huge industrial size reactor. Electricity cost is another one of the challenges with, I guess I may not have that scanned. Electricity costs are another one of the challenges of UV that, for big treatment plants, like they have UV reactors in New York City. And they are using just enormous quantities of electricity to treat all of the water that's consumed in New York City with UV. It can be on the order of tens of thousands of dollars a day in electrical costs. So that's just a little bit about like the calculation considerations. Is you have to think about, like, as a water particle is flowing through, whether it's close to the lamp or far away from the lamp, what intensity would it experience, and if you're trying to go for a certain dose. In this case, we're assuming it's far away from the lamp for the entire 1 second that it flows through the reactor. But of course, the particle could spend longer, and that's good as far as dose goes. But it's possible that the particle could go through the reactor faster than 1 second. Hopefully, if it did, it would be closer to the lamp where the intensity is higher. But I have an old classmate from when I was at Purdue, and he spent most of his career working at a company in New York that takes UV reactors, and they do really sophisticated experiments to try and find out what the dose is that when water flows through it, they're able to put in these little beads that get exposed to the UV and then collect them and sample how much intensity the beads absorbed as they flowed through the reactor. And you can also use like computer models to assess the flow trajectory through the reactors. This is just a look at the sleeve fouling that can accumulate, and it's basically it looks like glass, but it's not actually glass. It's made out of quartz. The difference being that quartz can transmit UV, whereas just ordinary glass will absorb UV. So, like your car window, you don't generally get a sunburn if you're inside of a car. You can sometimes get a little bit of UVA through the window, but UVC doesn't pass through glass, but it does pass through quartz. So this is a special, very pure silicon dioxide that the UV is able to pass through, but not if there's, in this case you can see it's orange because there was some accumulation of like iron deposits on this lamp sleeve as it was treating the water. So disinfection is one of the last steps in the water treatment process, but there are some things that they have to do depending on the location. There are cases where the water may be corrosive because it has so little mineral content that it could cause pitting of the pipes that are carrying water towards the people who are consuming it. And so sometimes after water treatment is completed, they'll have to add additional minerals to it. And calcium carbonate, if the concentration of calcium carbonate is too low, then it can cause pitting in the distribution network. But if you have too much calcium carbonate, then it can precipitate and cause deposition onto the pipes. And so there's just kind of like this range of acceptable calcium carbonate, and if you've got too little or too much, then you either have to, in the case of too much minerals, the typical approach there would be to add phosphate chemicals that help to prevent precipitation, and they just keep the minerals suspended in the water or dissolved in the water, or remineralizing water if it's too lean, as they say. So recarbonation is adding additional carbonate to it, and if there's too much, you could change the pH through acid addition, adding phosphate. Aeration is a way to force precipitation prior to the water entering the pipe. If you just aerate water in the storage tank, then it can force some of the minerals to oxidize in a location that would be less detrimental than they're precipitating into the pipe network. And adding alkali is just another pH addition measure that can get the water in the right pH range so that it doesn't precipitate in the pipes. Fluoride is in the news recently. I just heard this morning as I was driving to work that the governor of Utah is thinking about signing a bill that would ban the addition of fluoride to water. So for decades, fluoride has been added to water as a way of strengthening tooth enamel and helping to prevent tooth decay, and it can also strengthen the matrix of the bones as well. The fluoride that gets into the bones just makes them stronger. But too much fluoride can cause fluorosis, and I've already showed you some pictures of the modeling. It just kind of looks like yellowing of the teeth. And it's not necessarily that they're rotting, it's just that instead of looking white, they look mottled. Some of the opponents of fluoride have wild theories that it's detrimental to health. I haven't followed all of the pseudoscience behind the concerns, but I think it's generally accepted that in the concentrations that fluoride is added to drinking water, that it improves dental health and doesn't have widespread health effects in a negative sense. There's a lot of places where fluoride is naturally occurring. Sometimes if there's too much fluoride in the water, then they'll try and remove it. Usually ion exchange is used as the way of removing the excess fluoride. If it's more than 1.5 milligrams per liter, then that's when it can cause actually the yellow mottling of the teeth. And then when it's below 0.4 milligrams per liter, then it's oftentimes added as a way of providing preventative dental protection to children in particular. It's when children are developing that there's the most benefit to having fluoride in the water. So a lot of people have fluoride in their toothpaste. It does a similar thing. It helps to reinforce the matrix of the enamel in the teeth and make the enamel stronger. Sometimes there may be a need to treat finished water with exposure to activated carbon. And sometimes here in Huntington, if you look here on 3rd Avenue, there's a truck that passes through. I've seen it a lot of times over the years. It says Calgon on the side. And Calgon is just a company that makes water filters, and they are a supplier of activated carbon that can be used to absorb chemicals that are in water. And so in the springtime in particular, when farmers are applying pesticides to their fields, and it may get into the drinking water if they're applying pesticides and then there's a sudden rain that washes it off the fields and off their plants and gets into the river, then activated carbon can be a way to remove those pesticides before it gets into the drinking water. So it works through the process of adsorption. And absorption is just that the carbon-containing molecules are more greatly attracted to the activated charcoal surface than they are to staying in solution. And so the adsorbent is the activated charcoal that maybe, during certain seasonal periods, water would be flowing through a treatment plant with activated charcoal. Some people have it at their house all the time in those little Brita pitchers, or I have a carbon block filter on my faucet in the kitchen at home. Just it improves the taste of water if you run it through an activated charcoal filter, because it'll remove any impurities that are attracted to the carbon. Also removes any residual chlorine, which can have an effect on the flavor as well. Powdered or granulated activated carbon can be added to sand filters, or it can be a standalone process that's used after filtration. Sometimes they'll use even finer particulate powdered activated carbon, and it could just be shoveled into the water or metered out, and then it would be removed in a settling chamber, just like the flocks would after coagulation. So here's a look at how they're adding the granulated activated carbon to a sand filter, and it's less dense than sand grains, and so it would typically be the top layer in a sand filter. And here you can see these are the the troughs that are used during the backwashing process to capture the water that's going to be wasted during the bed fluidization. Here's some standalone carbon filter units. I think I told you that I took a tour when I was an undergraduate student of a community that had been big into explosives production during World War II. It was, they manufactured an explosive there, I think, called RDX, and it got into the groundwater, and so then they had to, for decades afterwards, they had to treat the water through activated carbon to get the explosives out. It wasn't at risk of blowing up, but it's not a good chemical for people to be drinking, and so they had to use carbon filtration to remove the RDX from the water. So it can improve the taste and odor, and when you're just using granulated or powdered activated carbon to improve the aesthetics, you can get a lot of use out of it. If it's not saturated, then the carbon can act for a pretty long time. If you're removing synthetic organic chemicals that are maybe pesticides, or for example, there was a spill of MCHM. You may remember that was in the introductory assignment. I asked you about MCHM, which was that coal washing chemical that's used here in West Virginia, and it spilled into the Elk River a few years ago, and people in Charleston were especially affected when they had to stop using their tap water for a couple of weeks and just relied on bottled water only, or water that was coming from the National Guard. So that's kind of when I installed a carbon block filter at my house, was during that Elk River spill, because that one, just coincidentally, it had a flavor associated with it. They said that MCHM kind of had a licorice flavor to it, and you could taste it in the water. But there may be synthetic organic chemicals that get into the water and aren't removed, and we're not able to taste them. And so I just figured maybe better to be safe than sorry and put a carbon filter on my drinking water. It can also, the activated carbon can be effective at removing disinfection byproduct precursors. And when you're using it for that, rather than just the aesthetic flavor improvements of water, then your activated carbon doesn't last quite as long. And it can be regenerated. Like, they can take the activated carbon and heat it up, and that causes the organic chemicals that are sorbed onto the outside to become airborne. They volatilize and they just go into the atmosphere, and then you could reuse the carbon again another time. Some disinfection byproducts like trihalomethane will saturate the activated carbon even more quickly than the disinfection byproducts precursors. So the organic materials, before they have been oxidized, won't use up a activated carbon filter quite as quickly as after they have been oxidized. So the disinfection byproducts themselves, you have to regenerate the filter a lot more quickly if that's what you're removing. Okay, so let me give you the handout associated with the project, and I'm also going to bring it up on the screen here, show you a couple of things. You may have, I don't know what kind of alerts you get on Blackboard, but do you get an alert every time I post some new item on Blackboard? It's probably depending on what your settings are. But yesterday is when I put these online, and there's a link that's available now having to do with selecting your topic. So let me give you this handout. I've created a list of topics that you can give some thought to and choose what you want to do for your research. And if you have a topic that you're interested in that you think maybe would be a good fit, you can let me know. You can propose an alternate topic. The topics are on the back side of this paper that I'm giving you now. Okay, so the project is 3 components. Part 1 of the project, which you have to submit by Monday, March 31st, is looking at, like, what are the current practices, what's known right now like what's the current aspect of the topic. So let's just look at some of these example topics. So the topic may be in situ vitrification. Does anybody know what that is? What that is if there's pollution, let's say somebody spilled dry cleaning fluid into soil. It's bad if that dry cleaning fluid gets down into the drinking water. And so if you have a pollutant, one of the ways to immobilize it is to take 2 electrical probes and then send a huge charge and basically turn the soil into glass. And so in situ vitrification is a way to try and trap a pollutant by turning the soil that it's in into a solid block of glass. So that's what in situ vitrification is. So part 1 of the project is do some research and write 3-page report minimum plus citations describing like what are the current practices, what's the current technology that's being used now, how is it developed, and so on. And that's what's due by the 31st of March. So you've got a little bit more than a month to write 3 pages. And of course, I do explicitly mention it in the instructions, but I'll tell you now as well that you shouldn't use generative AI to do the writing. It should be your writing, not ChatGPT. I don't want to read ChatGPT. I will be screening for whether it's written by a human or written by AI. But part 1 is a 3-page minimum report where you're also going to be, plus citations. So you should use the APA method of citation, which is, author, date in the body text, and then a list of references that you've cited after the write-up. Part 2 of the project is to look more at what is the future direction in your topic. So not what's the current practice, but what kind of research have people been doing to try and improve it? And so like back to the example of in situ vitrification. Like what kind of research have they been doing lately? Have they been looking at different types of chemical and their suitability? Have they been looking at ways to reduce the amount of electricity to cause the vitrification? Just, I don't know. For a variety of different topics, you can look over the topics before you decide which one you're going to do. But in part 2, you're going to look at several different research projects that have been going on recently and try and identify the common theme. And so I don't want you just to tell me about 4 or 5 individual papers that you saw. It should be a minimum of 4 peer-reviewed journal articles that you cite. But there should be some cohesive narrative. And so your topic may be, for example, noise pollution. And so for part 2 of the research paper, you're not just summarizing 4 research papers you found about noise pollution, but it might be that all 4 of them were talking about improvements in the way to measure noise pollution. And so, there may be some aspect of where most of the research is trying to improve a certain thing or deal with the challenge that exists in the area right now. And you won't necessarily know that until you start reading some of the references. And so you see that there's a big list of topics, and of course you can propose another topic and let me know if you want to choose something else. Once you know which topic you're going to choose, then you can select it with this website. There's just a survey where you'll put in your name, and then there's a drop-down list of topics. And each topic can only be selected by up to 2 students. And so, for example, only 2 students can use nuclear power and waste. And once 2 people have selected it, then it's going to be dropped off this list. It won't be visible anymore. So I've set it up so that each topic can only be selected by 2 students. Please don't pick a topic and then change your mind. Only pick it when you know what you want. And if you decide to pivot later on down the road, then you'll need to let me know so that I can make the topic available again to someone else. So my suggestion is to take these topics and maybe do just some preliminary research. You could look at, Wikipedia or ask AI about it. You'd ask AI, hey, tell me about eutrophication. Learn about it, and if it seems interesting to you, then sign up for the topic. And we're going to talk just a little bit more in a future class meeting about some ways that you can find good research papers. So we'll go to the library website and put in a couple of topics, and I'll just show you how you can find good peer-reviewed journal articles. Keep in mind that these are minimums, so you shouldn't expect a perfect score on the project if you do the minimum length and the minimum number of citations. So, you know, if you do the minimum, then maybe that's good for a C or a B minus or something. But the third part of this project is going to be that there will be a presentation. And so if you look at the class schedule for the semester, the last week of our semester is project presentations. And so you'll just give like a 5-minute presentation about your topic one of the days of the last week of class. And there's one of the things that we have to do in this class for our ABET accreditation is, you know, you have to practice and demonstrate communication fluency, and that's both written communication and also verbal communication as well. So I know most of you have already taken a speech class at Marshall, and this will be a good chance for you to use some of those skills that you learned in your communications speech class during the presentations. And so, yeah, read these handouts describing the project. If you know which topic you want to go for, then fill out the survey, and if you've got any questions, just let me know.